So let us come back. We have already done the bromination reaction of phenol. So now let us come back and see one reasoning question of alkylation and acylation of phenol. So in the exam, if this is given to you, Friedal-Crafts reaction, we very well know Friedal-Crafts reaction is of two types, correct? One is alkylation and one is acylation. So basically, phenol, if it is Friedal-Crafts alkylation reaction, Friedal-Crafts alkylation reaction, I'm just writing it as alkylation here. And when I speak about Friedal-Crafts acylation reaction, just remember phenol, so that means in alkylation you're going to add CH3Cl, in acylation you're going to add CH3COCl, correct? RCOCl. Remember, phenol does not show Friedal-Crafts alkylation reaction, right? Remember, so in the exam if this is given, just write no reaction. When I'm doing my reasoning questions, I'll explain why it is not showing, why aniline also doesn't show Friedal-Crafts alkylation reaction. But when it is acylation reaction, basically you're going to find two types of products. Let me show you that. So in acylation of phenol, what is the nature of phenol? This OH, whatever is there, it is a bidentate nucleophile. That means bidentate nucleophile. What does that mean? Bidentate means two sides. It can attack from both the sides. It can use this side as attacking in this also, this side also. So this whole phenol, basically, if I speak, it is a bidentate nucleophile. It can attack, means this particular AR can attack from this side, this ROCl, and from the other side. I'll show you that. So because of this bidentate nucleophile nature, what happens is when phenol is, or when it is made to attack with your RCOCl, instead of CH3 I'm going to take as RCOCl. So what happens is this phenol will show me, or it will give me two different products. How does it attack? Just see, this is your phenol ring, correct? Yeah. Now your OH is here and this particular thing is going to cleave here. This is your electrophile, this is your nucleophile. It's going to show me C double bond O and R. This is one product. Yes, this is one product. And the other product is phenol is going to show me one more product where, just both, you'll get an ester. Just see, you get an ester. So yeah, this is the ester. You're not finding an ester formation, you will find an ester formation. So what happens is, basically in alkylation there is no reaction for phenol, but in acylation it's going to show me two products. This is one product and this is one product. Finally, when I observe the structure, it's going to give me ester when it is reacting with acylation group. So we call it as C acylation, A acylation basically. C acylation is something called, this is called C acylation. We don't have in your syllabus, but I'm just mentioning it. This is called C acylation. This is called A acylation. What is that? C acylation, A acylation. C acylation is basically electrophilic aromatic substitution reactions, and C acylation is nucleophilic acyl substitution. This is called electrophilic aromatic substitution, and this is called nucleophilic acyl substitution. Just remember, this will not undergo alkylation, but if it undergoes acylation, these are the two products. One is this electrophile attacking, the other thing is nucleophilic acyl substitution reactions, where we get an ester reaction. Yes, so remember this. So please note it. Yes, and now after this, let us go back and do one more reaction of phenol, that is your nitration reaction. Remember, phenol, as I said, it's an OH group. OH is strongly electron donating, and it is going to give me ortho product and para product, correct? Now let us see. Now I'm going to take phenol, so let us write this heading, nitration of phenol, right? So when I'm going to take this phenol, yeah, and in the paper, if you find dilute HNO3, yes, at 20% or 20 degrees centigrade, and if you find concentrated HNO3, right, both, correct, concentrated HNO3 along with sulfuric acid is a nitrating mixture. This concentrated HNO3 or dilute HNO3, what is electrophile it is going to give us, or what is electrophile which is attacking? NO2 plus, right? NO2 plus is an electrophile. Correct? Here also it is NO2 plus is an electrophile. Now what happens is, at dilute HNO3 at 20 degrees centigrade, yeah, it's very dilute, isn't it? So the attack of this electrophile attacks at two positions. But remember, dilute, the electrophile is this, it's going to attack at two positions. Now one is at ortho position, one is at para position. Okay, one is at ortho, one is at para position. Yes, now this is your ortho nitrophenol and this is your para nitrophenol, correct? Now, when it is your concentrated nitric acid along with the nitrating mixture, rather nitric acid and sulfuric acid, at a stretch you get all the three occupied. What that is? 2, 4, 6. All the three are occupied. That is 2, 4, 6. Tribromophenol. Tribromophenol, or it is also called as picric acid. Picric acid. Yes. Right. Now observe carefully. What is the reason? Let us see the reason. Now here, if I speak, here it is a dilute condition, here it is a concentrated condition. So immediately the site is opened up and all the three sites which are ortho, para and ortho positions opened up, and the incoming electrophile has come and attacked. Fine. But now in the exam, if they ask you compared to ortho and para, which is a major product? Because in the earlier reaction bromination, what did I say? Para is more stable. But here, if I compare ortho and para nitrophenol, this is a major product and this is a minor product. Remember that. I'll explain the reason. Please note it. For dilute, you get ortho and para. For concentrated, you get 2, 4, 6 tribromophenol at a stretch. Remember that. Earlier in bromination, aqueous bromine will give you 2, 4, 6. Bromine and carbon disulfide will give you ortho and para product. Okay. Let us come back and reason this. So this is the question. Yes. So now what question may be asked from this? They may ask you in nitration of phenol, which is the major product? Which is the major product? So what did I answer just now? I said ortho is the major product, correct? We have to reason that. So you will write like this, just write. Right, I am writing now ortho nitrophenol. Here I will be writing para nitrophenol. Okay, I just wrote that NO2 plus. Here I have written. Yes. Now observe carefully. Here what happens in orthonitrophenol, when I said this is a major product, isn't it? This is major, this is minor. Correct? And now what is the reason? Simple. As you've seen, what are you observing? In orthonitrophenol, there is a formation of hydrogen bond in between oxygen and hydrogen. Yes. So what is happening? There is a formation of hydrogen bond. What type of hydrogen bond is this? This is intra. Intra means within the molecule. There is intramolecular hydrogen bonding. Intramolecular hydrogen bonding. Here what happened? Yes, here what happened? You have this para nitrophenol. So this is one molecule, this becomes reverse. Just see, this bonds with one more nitro group forming. Now here what happened here? You have this nitro, on the other side you have your H and OH. So what did I show you? Let us understand again. Here in this case you are finding hydrogen bonding within the molecule, so I call it as intramolecular. But here I am finding hydrogen bonding, but it is found in between two molecules. That's why this is called intermolecular hydrogen bond. Inter means between, intermolecular hydrogen bonding. So because of this reason, yes, so what happened? Which is stronger? Yeah, this is stronger, isn't it? This is very strong and this is more preferred, more stable. So this is a bit, compared to this is a bit less stable. So we always say this is more strong and this is highly preferred product. Let me reason again. Compared to orthonitrophenol and paranitrophenol, which is the most preferred product, this is a major product. So I wrote MJ. So let me write major product. Why is this major product? Because of intramolecular hydrogen bonding, which makes it more stable. Hence it is highly preferred. And this shows intermolecular hydrogen bonding, hence it is less preferred because less stable than compared to this. This is how you are going to reason the question.